Hi, everyone. I'm Evan McDonough. I'm a professor at the University of Winnipeg. I'm happy to be here at the Cosmology from Home conference. I want to thank the organizers and all of the participants for joining. This is great, and I'm glad we're all doing this together. Today, I'm going to speak about the π-Axion and the π-Axiverse. This is a scenario that was built in two papers, one from a few months ago with collaborators at Brown University, Stefan Alexander, Humberto Gilmer and Tucker Manton, and a paper from 2022 with Azadem Leknishad. Before I get started, I'll mention that right now I'm recruiting master's students to join my group. This is to start not this fall, but the following fall. If you want to share that with your colleagues and all your students, I'm happy to chat anytime. I think we do a lot of exciting work, and I'm happy to be growing the group. Okay, the plan for today. One, let's talk about axions, where they came from and where they're going. And I'll introduce this idea of the π-Axiverse and π-Axion dark matter. I'll discuss the experimental arenas and then conclude with a comparison of π-Axions and regular axions. I'll just make sure I have time here. Okay, so the next 15 minutes or so, we're going to crash course through all of this. So where did axions come from? Starting in the late 1970s, it all starts with the strong CP problem of the standard model, which is essentially the question of why is this number so small? This phase that accompanies this CP violating term, in principle, this could be order 1, it could be anything, but we observe it to be negligibly small. So by numerous authors in the early 70s put forward a dynamical mechanism to resolve the strong CP problem, right? Introducing a complex scalar field with a symmetry breaking potential, so that the phase of this complex scalar, a Goldstone boson of the global U1 symmetry breaking, can also couple to the gluon field strength. And it has a potential generated by instanton effects that dynamically sets the CP violating phase to 0. Now, around the same time, there was alternative scenarios put forward built upon composite degrees of freedom, a composite axion. And this is very closely related to what I'm going to be talking about today. Now, whereas this original composite axion scenario was aiming to solve the strong CP problem, and their mechanism to do so was to have dark quarks that are charged under both the standard model and a dark color force with new heavy degrees of freedom as well. Our approach is instead ask, out of a theory of composite degrees of freedom like pions, where can we find dark matter and dark energy? So let's talk a bit about axion dark matter. So the simplest setup is to take that complex scalar, the axion is the phase, you have some cosine potential coming from non-perturbative effects. Cosmologically, you have a Klein coordinate equation, and the cosmological evolution that at early times, the field is stuck in place by Hubble friction. Eventually, it rolls down its potential and starts to oscillate. And in this phase, it redshifts like 10⁻3, so like cold dark matter. The relic density of the axion dark matter is set implicitly by its initial condition. This initial value for the field, or in the sense that it's an angle, this initial misalignment. In a modern context, axions are abundant in string theory. We refer to these more generally as axion-like particles, and these comprise the string Axiverse. The simplest version of this story and the reason for the existence of this Axiverse is that gauge invariance of p-form fields in higher dimensions descends down to shift symmetries in 4 dimensions. So I have some b mu nu rank 2 tensor field. I dimensionally reduce this, for example, on some sphere, and I end up with an axion field where the gauge invariance of b mu nu is the shift symmetry of the axion. And for every type of field you have in string theory, and for every cycle I can integrate over in my internal space, I get an axion. And so in this way, I can get tens of hundreds of axions out of string theory compactification. But now I want to shift gears and talk about the π-Axiverse. Now, pions, I'd like to remind everyone, are at this point in time textbook physics. And in fact, if you look at the textbook sections on this, it's a lot like axions. So whereas the usual axion is to take a complex scalar and the axion is the phase, here, let me just promote this phase to be a sum over pions and the chiral symmetry generators. So for example, in a dark QCD with NF flavors, these are the generators of SU and F. The scalar potential at low energies that's generated for the pions. If I take the simple case where I have to generate pion masses, this really does just reduce down to a cosine potential, just like for a regular axion. The energy scales involved in the theory of the pions encode the energy scales in the theory of quarks. So the dark QCD scale sets the pion decay constant up to a factor of 4 pi. And the quark mass and the QCD scale together set pion mass. Now, if we have pion masses which are sub eV and decay constants which are relatively large, I can get axion dark matter-like cosmological evolution. And it's this that we refer to as π-Axion. The context in which we're thinking about this is a dark standard model. And there's 2 key points. One is we're assuming the presence of 2 energy scales in the model. 1 sets the quark masses, and 2 sets the QCD scale. And we're benchmarking every other scale in the standard model to the dark QCD scale, such as the Higgs Fib. Now, point 2, the coupling to the standard model, we're taking the dark photon and the standard model photon to have a kinetic mixing. And so it's the QED sector, which couples the standard model and the dark standard model. And this photon kinetic mixing serves to generate millicharges of all the dark particles, such as the dark charged pion. Now let's look at the pion sector of the theory. This is also now a textbook level analysis. You take your pions and your generators, and you can turn the crank and calculate what is the spectrum, what are the masses of every pion in the theory, and including the electromagnetic contribution, which depends on the decay constant and the charge. And what you get out of this, here I'm considering dark QCD, where all 6 flavors of quark are light. So unlike our standard model, where you really only have 2 light flavors, here we're saying all 6 flavors of quark are benchmarked at the scale MQ. The spectrum that you get out is you have 5 real neutral scalars, you have 6 complex neutral scalars, and 9 charged scalars. These are like the charged pion, complex neutrals like the kaons of the standard model, and these are like the neutral pion. One way to understand this is to just plot it out. This is a plot of the distribution of masses because of the number of pions at each mass range, with some assumptions as to how much the masses are allowed to fluctuate within each generation. 3 generations of quarks, and there's some small mass splitting in each generation. And the general picture that you see is bumps in the mass spectrum. Here I'm looking at charged and neutral and neutral complex pions. So you have some, relatively complicated structure to the mass spectrum spanning over, about a decade in masses, a factor of 10 roughly. So let's look at the portal to the standard model. As I mentioned here, we're considering kinetic mixing between the dark and standard model photons. And the role of this is to generate millicharges for all the dark fermions. And in particular, or not only for the dark, it generates millicharges for the dark quarks, which gives millicharges to the charged π-Axions. So similar to a standard model or the standard axion story, I get this anomalous coupling to phi ff tilde. Right here, the phi here is pi 0. And in contrast with the axion, it comes with epsilon squared. That's encoding the millicharge. I also have the standard interaction from scalar QED, where pi plus minus is a charged pion, and this is simply describing the charge of the charged pion. And then from integrating out the dark electroweak sector, I also have flavor violating interactions which couple pions to the photon. And I'll note at this point that the lifetime of the neutral pions, if I have axion-like masses and axion-like decay constants, even for epsilon is order 1, it is easily cosmologically stable. If I'm thinking of f pi is 10 to the 10 GeV, this is a ginormous lifetime for the neutral pion, even if epsilon is equal to 1. I'd also like to note the connection to the WIMPzilla paradigm. In this context, you have this dark QCD theory, and you can work out the spectrum of pions, but you also have the whole rest of the 7 degrees of freedom at low energies in QCD, such as the baryon. And these two sectors are connected by the same underlying QCD parameters. So whereas the QCD scale sets the decay constant of the pions, it sets the mass scale of the baryons. And for the last several decades, there's been a wealth of mechanisms developed to produce a relic density of such heavy particles, such as gravitationally or by freezing. So both of these approaches can give you some fraction of the relic density of dark matter being in the baryons. So you do have this complementarity between heavy and light degrees of freedom in your dark sector. Okay, let's think about the experimental arenas where we can test the π-Axiverse. So first off is the parity-odd portal, which is the standard approach to axion direct detection, and there's billions of dollars being spent on this approach. The neutral π-Axions couple to the photon via this vertex with a coupling that scales like epsilon squared over the decay constant. So this epsilon, if I'm thinking about small millicharges, this can be a significant suppression, which distinguishes this from the regular axion. But again, I'll note you can have epsilon is equal to 1, and this does not impact the stability of the neutral pion. One aspect it does enter into, which I won't have time to talk about today, but if I have epsilon order 1, it generates a large mass splitting, so very heavy charged pion. And that's something we can talk more in detail maybe in the discussion section. But I'll note the essential prediction of the π-Axiverse here is that I should have 5, for the 5 neutral π-Axions in my dark QCD, I should have multiple distinct resonances mapping out the spectrum of masses. I also have the parity-even portal, which is coming from the neutral complex π-Axions and also the charged π-Axions. So we have this coupling to the field strength. And there's a very nice paper here which shows how you can use atomic clocks as a way to measure the fine structure constant, and this encodes the coupling to the photon field strength. And so what the result is that you have an oscillatory contribution to this, and given certain benchmark values of parameters, this can be observable. And if we're thinking about, for example, the fuzzy π-Axion limit, this becomes, you hit the observable range when you look at tiny gauge couplings of the dark electroweak. Or if I can relax the Higgs mass, then I can relax this range of the coupling. So there's a relatively rich parameter space that can be constrained by atomic clock experiments. Finally, I'd like to note the somewhat exotic possibility that you can have π-Axion stars and that those stars could explode. And these π-Axion star explosions, worked out by other authors in these nice papers, the mechanism for this is a parametric resonance of photons. So here, what I'm showing is simply the equation of motion for the helicity states of the photon field, or Fourier modes of the plus and minus helicity states of the photon field. And the only takeaway point for the moment is that I have oscillatory contributions to the mass, which when I have this whole effective field theory of all the interactions with the photon, takes on a set of sums over all the interactions in all the pion species. So I have many, many sources of resonance, which all contribute to this instability of π-Axion stars. And I'll note that path work, considering only the scalar QCD coupling, really can be incredibly efficient. So you put all these things together, you are really ramping up π-Axion star explosions. Okay, let's wrap this up. And what I'd like to do first is to emphasize some of the differences between a π-Axion and more conventional axions. So the π-Axion, we're thinking of confining gauge theory, and you have chiral symmetry breaking. The π-Axions are the Goldstone bosons of chiral symmetry breaking. The conventional axion is a Goldstone boson of a global U1 symmetry, and it comes from the phase of complex scalar. So for the axion, I get one axion per complex scalar. Whereas the π-Axion, I get many pions. And I have a mass splitting that I can calculate, and it's due to the masses of the quarks and the masses of the electromagnetic splitting due to the coupling to photon. Both the conventional axion and the π-Axion have their WIMPzillas. So in that regular axion case, you have the radial field, the magnitude of this complex scalar. In the π-Axion, you have the dark baryons. In the In the axion case, you have this one real neutral scalar, pseudoscalar rather. In the π-Axion case, you have both real and complex neutral degrees of freedom, and also the charged degrees of freedom, like the charged pion. Both the π-Axion and the axion have an abundance of other degrees of freedom. In the axion story, it's model dependent. In the π-Axion story, from this dark center model, we have the whole dark electroweak sector. You have blue balls. You have lots to play with there that you can go searching for, which again encodes the same, some relatively small step underlying parameters. In the axion case, you have parity-odd couplings of the axion to photons. In the π-Axion, you have both parity-odd and parity-even couplings. For example, the coupling of the charged pions. Okay, my last remaining minute here, I want to answer this question. So what are the smoking guns of π-Axions? What should we be looking for? One is this combination of parity-odd and parity-even couplings, and they're benchmarked to the millicharge and the decay constant. Two, you have heavy dark baryons with mass that's roughly equal to the decay constant. And three, I think in all of these windows, what you should search for is the spectrum of π-Axions, which is calculable using standard QCD techniques. And the general expectation is a tightly packed discretum of signals, then mapping out the masses, boom, 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 of the π-Axions. And with that, I'll say thanks. Bye.